Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In today's lecture, we focus on the effect of friction on the pressure in the suction pipe and delivery pipe. In the previous classes, we have studied the effect of acceleration of piston on the pressure in suction pipe and delivery pipe. Now, the effect of friction loss on the pressure in suction pipe and delivery pipe. You all know that the friction loss is calculated using the equation, the Darcy-Weisbach equation. HF is equal to FLV squared by 2GD. V is not uniform. The velocity in suction pipe or delivery pipe is not uniform. How or the variation of velocity will be that we have derived already. So the velocity in the pipe can be given by an equation capital A by small a omega r sine theta, where capital A is the area of cylinder, small a is area of suction pipe or delivery pipe, and omega is the angular speed and theta is the angle made by the crank. So depending upon the angle made by the crank, the loss changes. The important thing here is the head loss due to friction is equal to FL by 2GD into A by A omega R sine theta whole square. That means it varies with the square of the head loss varies with the square of the velocity. That itself shows that it is not a linear variation, it is a parabolic variation. So these things, if you note it now, let us go into straight the topic. Effect of friction loss on pressure in suction pipe and delivery pipe. You know that the friction loss equation is equal to FL V square by 2GD. V is the velocity in suction pipe or delivery pipe, whichever you consider. L is the length of suction pipe or delivery pipe. Better let us use small l. P is the diameter of suction pipe or delivery pipe. F is the friction factor. We know the velocity in suction pipe or delivery pipe varies as follows. How it varies? Small v is equal to A by A omega r sine theta. Therefore, HF is equal to FL by 2GD into A by A omega r sine theta whole square. So this is the equation for the friction loss. If I observe here, HF is proportional to the square of theta. That is, variation is parabolic. How it will be? Let us take any of the things. So therefore, what is HFS is equal to F length of suction pipe to 2G ds into A by AS omega r sine theta whole square. Delivery pipe is equal to FLD divided by 2G A by AD omega r sine theta whole square. So this is the values. Now we will take suction stroke. If I take suction stroke, beginning theta is equal to 0 degrees, then what will happen to HFS? FLS by 2GDS into A by AS omega r sine 0 whole square. So sine 0 is equal to 0. So therefore HFS is equal to 0. That theta is equal to 90. That is at the middle. This is beginning, middle. HFS is equal to FLS by 2GDS A by AS omega r sine 90 whole square. Sine 90 1. So therefore HFS is equal to FLS by 2GDS into A by AS into omega r whole square. This is the number. And theta is equal to 180 degrees. End of suction stroke. HFS is equal to FLS by 2GDS into A by AS into omega r sine 180 whole square. Sine 180 is equal to 0. So it is equal to basically HFS is equal to 0. So final conclusion is beginning HFS is equal to 0. Middle FLS by 2GDS into A by AS omega r whole square. End of the stroke. HFS is equal to 0. So this is the first thing. Let me go into the second thing. Delivery stroke. Again, beginning theta is equal to 0 degrees. So HFD is equal to FLD divided by 2GDD into A by AD omega r sine 0 degrees whole square. Sine 0, 0. Therefore, HFD is equal to 0. Theta is equal to 90. That is at the middle of the stroke. HFD is equal to FLD by 2GDD into A by AD omega r sine 90 whole square. Sine 90 is equal to 1. Therefore, FLT divided by 2GDD into A by AD omega r whole square. Theta is equal to 180 degrees. H of D is equal to FLD divided by 2GDD into A by AD omega r sine 180 whole square. This is equal to 0. Therefore, H of T is equal to 0. So we got three values also. So now we got variation and how they vary with the in the suction stroke and delivery stroke. Now let me go into the indicator diagram. Indicator diagram showing the friction loss also. So if I show like that, then what will happen? Let us see. So x-axis, y-axis, x-axis is stroke length, y-axis is the pressure head, right? And first thing is we will write atmospheric pressure head, H atmosphere. This is H atmosphere, which is equal to 10.3 meters of water. The diagram is this is how it is. It is HS, it is HD basically. Theta is equal to 0, theta is equal to 90, theta is equal to 180. Again, theta is equal to 0, theta is equal to 90, theta is equal to 180. This is the suction stroke, this is the delivery stroke, and this suction head is always less than this. This is the negative head actually, negative pressure head. Now on this what I want to do, I want to impose the friction. The friction, if I already mentioned, the variation is square. HF is the variation of theta. So square of theta. So it's a parabolic variation. At the beginning, we have already shown it is 0. At the end also it is 0. And it is a parabolic variation. And similarly in the delivery stroke also, it is a parabolic variation in this fashion. So this is the ordinate. So now this part, whatever I have shown is the friction basically. The central part is ideal indicator diagram and this part has come due to friction. So now if I take it actually at the beginning of suction stroke, if I write at the beginning theta is equal to 0 degrees. So total head is equal to HS. Total suction head is equal to HS because HFS is 0. At the middle, theta is equal to 90 degrees. The total suction head is equal to Hs plus Hfs, that is equal to Hs plus Fls by 2gds into A by As omega r whole square. Then at the end, theta is equal to 180 degrees. So total suction head is equal to Hs plus 0 only. So therefore it is equal to Hs. Same is the case if I write the delivery stroke. Beginning means theta is equal to 0 degrees. Total delivery head is equal to Hd because h of d is equal to 0. At theta is equal to 90. The total delivery head is equal to Hd plus Hfd, which is equal to Hd plus Fld by 2g into dd A by Ad omega r whole square. Theta is equal to 180 degrees. Total delivery head is equal to again Hd. So these are the three things. So once I obtain this, then what is the work done? The work done against friction. Against friction both in suction pipe and delivery pipe. If I calculate variation, already I told actually it's a parabola. If I take that as a parabola, so it is nothing but if you just see the figure actually, if I call it as AB basically, and this are ideal indicator diagram CD, then naturally, so this is EF, we have put atmospheric pressure. So I write it as G basically here, and this is H middle, then I write it as IJ, right? This is basic thing. So this part is HFS and this part is HFD. So if I move actually work done against friction is equal to the what we can write actually, it is basically the area of the parabolas. There are two parabolas actually. One is AGB and the other one is CID. These are the two parabolas. So what is area of AI? Area of AGB. Area of AGB, it's a parabolic area. So naturally base length is AB into 2/3 of the altitude, that is GB. Sorry. So the friction loss, the friction loss can be represented by a parabola in the indicator diagram. So that means during suction stroke, if I take it, this is how the loss will be. And this is theta is equal to 0 degrees. And this is theta is equal to 90 degrees. And this is equal to theta 180 degrees. And this is the friction loss during suction stroke. And this length is length of the suction stroke. Now basically the work done, rather than the work done per second is proportional to the area of indicator diagram. That means it is proportional to L into 2/3 of HFS, or work done per second is equal to K into 2 by 3 into L into HFS, and it is equal to gamma A n by 60 into 2 by 3 into L into HFS. Then what is HFS? Already we have derived. HFS is equal to F LS by 2G TS into A by A omega R whole square. This is the thing. So why this is parabolic actually? This is parabolic because HFS is proportional to the square of crank angle. So therefore, the work done per second during suction stroke is equal to, in suction stroke is equal to gamma A n by 60 into 2 by 3 into L into F LS by 2G ds into A by AS omega R square. This is the final thing, or the same can be repeated for delivery stroke. That delivery stroke, if I take the delivery stroke, so this is how it is. Theta is equal to 0 degrees, theta is equal to 90, theta is equal to 180. And this is how the variation. This is HFD. Again, basically, it is the, again, all that you can repeat it. Again, I can write work done per second in delivery stroke is equal to gamma A n by 60 into 2 by 3 into L F L D by 2G dd A by AD omega R whole square. So this is regarding the friction basically. So now I have completed the friction loss, and also what is the power expended during basically each stroke. So this is very, very important because this is only a starting point actually. Once we go into the next topic where we bring in the air vessels, so without air vessels, what is the power lost in friction? With air vessels, what is the power spent against friction? Then actually now that really makes us so much of power saving or the work done saving because of the introduction of the air vessels, which we will deal in the subsequent lectures. Thank you. Thank you very much.
Like, share, and subscribe. Hit the bell icon for more updates.